At the end of part 2, I asked you to think about what sort of test statistic, so a large one or a small one, would we expect to get if the null model was true, and what sort would we expect to get if the alternative model was true. And one way to think about this is to remind yourself that when we write expected here, we said previously that this is what we expect if the null hypothesis is true. So let's say the null hypothesis actually is true. Then in that case, what I observe should be pretty close to what I expected because I thought the null hypothesis was true, it actually is. My answers should be pretty close together. So when I take what I observe minus what I expect, I'll get a relatively small number, and I'll square that and it'll stay relatively small, I'll divide by something, and so my test statistic should actually end up being small. Now we don't know what small means at this point, but think about what if the alternative hypothesis was true. Now in that case, these numbers tell me what I expect if my two variables are not related at all, but they actually are related. So what I observe may not look anything like what I expected in that case. That means that the difference between what I observed and expected could be large, and I'm going to square it and get something that's also large, and I would get a big test statistic in those cases. And so that's exactly what we've got here in the notes, is that if the null hypothesis is true, what I observe should be close to what I expected in that case, and I would get a relatively small number. I also pointed out that the test statistic can't be negative because we're squaring that top part, the bottom part can't be negative, so everything is 0 or larger, all right? So null hypothesis is true, we expect a small test statistic. Alternative hypothesis is true, we expect a large test statistic. And we're going to come back to this when we think about our p-value and things like that later. But before we get into that, I want to pause for a second and think about the assumptions for a chi-squared test. So again, we're walking through this new type of hypothesis test. We've learned what sorts of problems we can answer with it, how to set up the hypotheses to test those things, and how to calculate a test statistic. Now our next step should be to look at a sampling distribution, use that to find a p-value, and then draw a conclusion. But just like every other test we've seen this semester, there are certain conditions that need to be true for this test to work the way that we want it to. Our conditions for the chi-squared test is that our data is a random sample from the population. So we've had this condition for every single test we've done. And then similar to the tests for population proportions, we need to make sure that our sample size is big enough. And that's fairly vague. When we talked about the questions related to population proportions from notes 13, we said that big enough had to do with our sample size times our sample proportion times 1 minus our sample proportion being bigger than or equal to 10. That's what we decided was going to be reasonable for us to decide that our sample size was big enough. For a chi-squared test, well, we've got this sort of table, we've got two variables, we can't use that same condition anymore. So what we're going to do is we're going to make sure that what I'm calling most, but we'll go with, say, at least 80% of the expected counts in our table are greater than or equal to 5. If that's true, we're going to say that our sample size is big enough and we can go ahead and do this problem and feel comfortable with our results that we get. All right? So even though we had a very similar condition in notes 13 when we talked about population proportions, remember that we've got different ways to check both of those. So you want to know which of these setups you're in, what type of question you're answering, to know how to check that assumption. So if we check those and we feel that things are reasonable, we can then go ahead and try to figure out what is the sampling distribution and how can we use that to get something like a p-value. All right. Couple things to pay attention to that I've briefly mentioned is the different ways of checking assumption 2 for notes 13 and notes 14. And then I also want to point out that it's possible if you've taken another statistics class where you've learned a chi-squared test, you may check assumption 2 slightly differently. I've seen other classes where they say that all of the cells of expected counts should be bigger than 5, and there might be other versions too. So we'll use this one for our class, but just keep in mind that this isn't universally agreed upon, just like it wasn't in Notes 13. So what is the sampling distribution for this chi-squared test? When we used the t-test statistic, we said that that followed a t-distribution. When we used a z-statistic, we said that that followed a standard normal distribution, which we also referred to as a z-distribution. And so it may not surprise you too much to learn that when we calculate a chi-squared test statistic, it will follow a chi-squared distribution. And just like the t-distribution, there's not just one chi-squared distribution, there's actually a lot of different chi-squared distributions, and they depend on degrees of freedom. So what we do to find the degrees of freedom for a chi-squared distribution is we take the number of rows minus 1, and we multiply it by the number of columns minus 1. So for the example that we've been working with, we said that that had 3 rows and 2 columns. So number of rows minus 1 would be 3 minus 1 is 2. Number of columns minus 1, 2 minus 1 is 1. So I would get 2 times 1, and I would say that that is a chi-squared distribution with 2 degrees of freedom for the sampling distribution. And so I've got a few pictures here with degrees of freedom of 2, like we said our example has, degrees of freedom of 10, and degrees of freedom of 100. And let's look at what the chi-squared distribution actually looks like. So I made these in StatKey. You'll get a chance to do something like this a little bit later. But you can see that this one looks right skewed. It's got a tail going out to the right-hand side. And it just sort of slopes down. When we have 10 degrees of freedom, this still looks right skewed, but it actually looks a little bit more like a bell curve. And so that's something that we might think about is, what's happening as the degrees of freedom get bigger. And you can actually see that with 100 degrees of freedom, this looks fairly bell-shaped. Now it might not look perfect, but essentially is as the degrees of freedom get bigger, it gets less and less right skewed and starts to look more bell-shaped. Right? So if we want to find p-values for this test, we are always going to shade to the right of our test statistic. And to think about why this would be, you can think back to how we ended the last part of the notes, where we talked about, well, what kind of test statistic do we get when the alternative hypothesis is true versus when the null is true? Now, remember that the sampling distributions that you see here, these would represent the types of test statistics we would get if the null model is true. To calculate our p-value, what we want is we want to know how likely, if the null model is true, would it be for us to get our test statistic or something more extreme. And if you think way back, we said more extreme depends on the alternative hypothesis. So if I would get big test statistics when the alternative is true, my p-value is going to start wherever my test statistic is, and then it's going to shade everything bigger than that value, because that represents things more extreme than what I've seen. So you can actually kind of reason through how we would shade for our p-value, even if you don't remember it and you need to kind of think of it fresh again. So we'll end part 3 of the notes here. When we pick up with part 4, we will look at how to actually find the p-value using StatKey, and then what sorts of conclusions we can make for our test depending on the results of our p-value.